Good morning students. Today we have lecture number 11. Today we shall solve one numerical and after that we will start the theory part. Only one numerical I will solve and after that we will start the theory part or next part of the syllabus. Okay. So next question, write down this next numerical NCERT book. So determine the electrostatic potential energy of a system consisting of two charges. Determine the electrostatic potential energy of a system consisting of two charges. 7 microcoulomb and minus 2 microcoulomb. 7 microcoulomb and minus 2 microcoulomb. 7 microcoulomb and minus 2 microcoulomb. Bracket, in the bracket you write down and with no external field close the bracket. Placed at bracket 9 centimeter, 0, 0, close the bracket. Placed at minus 9 centimeter, 0, 0 and 9 centimeter, 0, 0, close the bracket. Respectively, you please stop. Respectively, you please stop. This is complete one sentence. Here, once again I will read. Determine, say this as A. First, in the beginning you write it as A. I forgot. In the beginning you write it as A. Determine the electrostatic potential energy of system. Determine the electrostatic potential energy of a system consisting of two charges. 7 microcoulomb and minus 2 microcoulomb and with no external field. Is in the bracket. Placed at minus 9 centimeter, 0, 0 and 9 centimeter, 0 and 0. Respectively, you please stop. Next, write down next part of the question B. This part is A. Next part of the question B. How much work is required? To separate the two charges? How much work is required to separate the two charges infinitely away from each other? How much work is required to separate the two charges infinitely away from each other? Question mark. How much work is required to separate the two charges infinitely away from each other? Question mark. This is B. Next, write down C. Suppose the same system of charges. The same system of charges is now placed in an external electric field. Suppose the same system of charges is now placed in an external electric field. Suppose the same system of charges is now placed in an external electric field. Capital E is equal to A into 1 by R square. Capital E is equal to A into 1 by R square. A is equal to 9 into 10 to the power 5 coulomb per meter square. A is equal to 9 into 10 to the power 5 coulomb per meter square. Give list of. What would the electrostatic energy of the configuration be? What would the electrostatic energy of the configuration be? What would the electrostatic energy of the configuration be? Question mark. What would the electrostatic energy of the configuration be? Question mark. This is C. So totally there are 3 parts in this question, A, B, C. We shall solve one after another. So here, first one, 2 charges, that is 7 microcoulomb and minus 2 microcoulomb. 7 microcoulomb and minus 2 microcoulomb are placed at the points. One point is minus 9 centimeter 0 0 and another point is 9 centimeter 0 0. That means the distance between the 2 charges will be, what will be the distance between the 2 charges? By looking at the coordinates, you can tell distance between 2 charges. Distance between 2 charges will be, I will write directly. This is minus 9 centimeter means minus x axis. This is plus axis. So add them. So I will get so 18 centimeter. 18 centimeter, that is 0.18 meter. So that will be the distance between the 2 charges. So now 2 charges. Here I will just draw the diagram. 7 microcoulomb and another one is minus 2 microcoulomb, and they are separated by a distance of 0.18 meter. 0.18 meter. Then we have to find the potential energy of the system. First, we have to find what we have to find. We have to find determine the electrostatic potential energy of the system. So we know that electrostatic potential energy of system of 2 charges, is given by U is equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R12. What is R12? R12 is the distance between Q1 and Q2. This is Q1 and this is Q2, right? This is A, this is B, if you want, just for our understanding. All these things are for our understanding. So U is equal to 1 by 4 pi epsilon Q1 Q2 divided by R12. R12 is nothing but distance between them, that is 0.18. Now substitute the values. So U is equal to 9 into 10 to the power 9. Q1 is 7 into 10 to the power minus 6, 7 microcoulomb. And Q2 minus 2 into 10 to the power minus 6 coulomb, and divided by R12, that is 0.18 meter, 0.18 meter. So now simplify this and you will get the answer. I will tell the answer. On simplification you will get U is equal to, it will comes out to be negative, that minus 0.7 joule. Minus 0.7 joule. So potential energy of system of 2 charges is comes out to be minus 0.7 joule. Negative means it is stable system or unstable system. Think whether it is stable system or unstable system. When potential energy of the system of charges is negative, that means it is a stable system. It is not unstable. If electrostatic potential energy is positive, then it will be unstable. So it is a stable system because it is negative. Then work has to be done to break the system, because it is a stable system. So work has to be done to break the system. And B, they are asking that one only. B, what they are asking? How much work is required to separate the 2 charges infinitely away from each other? How much work is required to separate the 2 charges infinitely away from each other? That is nothing but work required to break the system. That is work required to break the system. Directly I will write to break the stable system. I will write stable system. Directly I am giving the formula. Okay, is equal to negative of potential energy of the system. Work required to break the stable system is equal to negative of potential energy of the system. Okay, otherwise I will solve like this. So we know that work required, I will solve in a different way. Okay, like that also you can solve. That is simple way. Another way also, work required to separate to separate the charges, is equal to change in potential energy. That is nothing but change in potential energy. Change in potential energy of charges. So that is work required to separate the charges from where to where? From final position to initial position. So UF2, UF minus UI. UF is final position. That is, this is initial position. Now they are at a distance of 0.18 meter. They have to be broken and separated so that they move to the infinite distance. So UF minus UI. UF is potential energy at the final position and UI is potential energy at the initial position. This is nothing but delta U. Delta U is nothing but change in potential energy. Delta U is nothing but change in potential energy. W work done is equal to change in potential energy, that we have already know. So UF, that is potential energy at the infinite, because finally these two are broken and finally sent to the infinite distance. So potential energy at the infinite distance is 0 minus potential energy at the initial position. Initial position is nothing but when the distance between them is 0.18 meter. When the distance between them is 0.18 meter, what is the potential energy of the system? It is nothing but 0.7 joule. It is minus 0.7 joule. So minus into minus plus. So W is equal to 0.7 joule. So this much amount of energy, this much work has to be done to break the system. To break the system, the work done is W is equal to 0.7 joule. That is positive work has to be done to break this system, because it is a stable system. It is a stable system. Understood? Got the idea? Okay, next third one, C. This is A, B, C. So now C. See what is there. Okay. See what it is. Suppose the same system of charges is now placed in an external field. That is E is equal to A into 1 by R square. They have given. And the value of A is 9 into 10 to the power 5 coulomb per meter square. So now the same system of charges, that is system of two charges is placed in an external electric field. Now then what would be the electrostatic energy of the configuration? That is the energy of the two system of charges in an external electric field. So we know that the potential energy of system of two charges, in an external electric field, is given by, that is U is equal to, we have already studied potential energy of system of two charges in an external electric field. We have studied, I think it is in the lecture number 7. It may be in the lecture number 7. Okay, check it out. Electrostatic potential energy of system of two charges in an external electric field is given by Q1 into V dash plus Q2 into V double dash plus 1 by 4 pi epsilon naught Q1 Q2 divided by R12. This is how we have determined the formula. We have determined this formula directly. Q1 into V dash plus Q2 into V double dash plus 1 by 4 pi epsilon Q1 Q2 divided by R12, where V dash and V double dash are the electric potential due to the external electric field. V dash is electric potential due to the external electric field at the point of Q1, and V double dash is the electric potential due to the external electric field at the point of Q2, and R12 is the distance between Q1 and Q2. So now from this we can find so electric potential due to external electric field, electric potential due to external electric field, that is V dash is equal to V double dash, both are equal here. So V dash or V double dash is equal to E into R. Electric field is given, so we know that that is E is equal to E is equal to V divided by R. E is equal to minus dV divided by dr. So for a small values of for small values and electric field is constant, then you can write E is equal to V by R. So V is equal to E into R. So V dash or V double dash is equal to E into R. E is nothing but external electric field, and external electric field is given as A into 1 by R square into R. So therefore this will becomes V dash or V double dash will be equal to so much A divided by R. A divided by R. So now substitute these values. So therefore substitute these values in that above equation. So in this equation, so substitute here. So we'll get U is equal to Q1. So V dash or V double dash is the electric potential due to the external electric field, that is comes out to be A by R, and A is nothing but that is also we know 9 into 10 to the power 5 divided by R. Okay, substitute this value here, V dash, V double dash. So and Q1, Q2 and all these things, this entire thing we have already calculated, we know that value also. So now I will substitute the value. So that is Q1. Q1 is 7 into 10 to the power minus 6. V dash. V dash is nothing but 9 into 10 to the power 5 divided by R. R is nothing but the distance between the two charges. Distance between the two charges, it is initial position. What was the initial position? R is initial position. Initial position, what was the initial position? Initial position of the system of charges, that is Q1. Initial position of Q1. Okay, what was it? Initial position of Q1, that is 9 centimeter, no? 9 centimeter. So you will write it as 0.09. 0.09. So Q1 into V double dash plus Q2. Q2 is minus 2 into 10 to the power minus 6 and V double dash, that is nothing but this one, 9 into 10 to the power 5 divided by R, that is the position, that is also 0.09. So plus this value 1 by 4 pi epsilon Q1 Q2 divided by R12. So this entire value we have already calculated it as minus 0.7. So now simplify this one, you will get the answer. I will directly write the answer. We will get the answer like this. I will tell the answer. Okay. So you will get the answer as like this. On simplification you will get 49.3 joule. U is equal to 49.3 joule. So this is the potential energy of system of two charges in an external electric field. 49.3 joule. This is the potential energy of system of these two charges in an external electric field. Understood? Okay. Solve such kind of numericals if you get somewhere. Okay. Next numerical, one homework you write. And next we will start the theory part. Next one homework you write. This is homework. You solve this one. Charges 2.0 into 10 to the power minus 6 coulomb. Charges 2.0 into 10 to the power minus 6 coulomb and 1.0 into 10 to the power minus 6 coulomb. Charges 2.0 into 10 to the power minus 6 coulomb and 1.0 into 10 to the power minus 6 coulomb are placed at corners. Capital A and capital B of a square. Charges 2.0 into 10 to the power minus 6 coulomb and 1.0 into 10 to the power minus 6 coulomb are placed at corners capital A and capital B of a square. Offside 5.0 centimeter. Offside 5.0 centimeter. As shown in figure. Figure is given. I will draw the figure. As shown in a figure. Cube list of, as shown in figure, cube list of how much work will be done. How much work will be done against the electric field. How much work will be done against the electric field in moving a charge. How much work will be done against the electric field in moving a charge of. How much work will be done against the electric field in moving a charge of 1.0 into 10 to the power minus 6 coulomb. How much work will be done against the electric field in moving a charge of 1.0 into 10 to the power minus 6 coulomb from C, from capital C to capital D, from capital C to capital D. How much work will be done against the electric field in moving a charge of 1.0 into 10 to the power minus 6 coulomb from capital C to capital D, question mark, from capital C to capital D. Draw the diagram. A, B, C, D. They have given, and at the point A, the charge Q1 is there, and at the point B, charge Q2 is there, and this distance is 5 centimeter. They have given. So we need to find out. We need to find out what work, how much work will be done against the electric field in moving a charge of 1.0 into 10 to the power minus 6 coulomb from C to D. From C to D. So from here to here, if you want to bring a charge, how much charge? That is 1.0 into 10 to the power minus 6 coulomb. This is the test charge. So this will be the test charge. These two will be the source charges. This charge has to be moved. Q0 has to be moved from C to D. Then what is the work done? You solve on your own. Then it will be good. Then it will be good. I have solved such kind of numericals, but not exactly such. So I have solved from one corner to center. How much work has to be done from one corner to center? I have solved. Let us see. You solve this one. Okay. So I will give the answer also. I will give the answer also. The answer will come so to be, the final answer, the work done will come so to be 0.053 joule. 0.053 joule. The answer for this question is 0.053 joule. The answer for this numerical will come so to be 0.053 joule. Solve that one. Okay. Okay. So these many numericals are enough. These all are the numericals that you have to learn under this chapter. See here, we can solve n number of numericals, large number of numericals, but बहुत कुछ सॉल्व कर सकते हैं, लेकिन अपना मतलब का सॉल्व करना बहुत इंपॉर्टेंट है. अपना मतलब का मीन्स द न्यूमेरिकल्स which will be important for our exams. So what type of questions they will ask in the exam, so relating to that I will be solving the numericals. I will not solve any numericals which are not relating to the exams. Okay. So next we will study about the theory part. Okay. Lecture number 11 on electric potential and capacitance. So far we have studied the electric potential and all the different concepts and the numericals also we have solved. So now today we shall study the new concept, that is behavior of conductors. Behavior of conductors in electrostatic field. Behavior of conductors in electrostatic field. So this is the next topic that we have to study, behavior of conductors in electrostatic field. So first let us understand what are conductors or insulators. So conductors are those materials which allow the electric charges to flow through them. Conductors are those materials which allow the electric charges to flow through them, whereas insulators does not allow the electric charges to flow through them. And we know that no material is perfectly conductor or perfectly insulator. Perfectly conductor or perfectly insulator is an ideal concept. Okay. So conductors will have large number of free electrons. The conductors will have large number of free electrons, and these electrons are free to move in the body of the conductor. These electrons are free to move in the interior of the conductor, and as well as they can be easily moved from the surface of the conductor with a little effort. But in the case of insulators, the charges are not free to move. That is, if a charge is given to a insulator, the charge remains static in the on the insulator. The charge remains static on the insulator. That is, they are not mobile charges. They are not mobile charges. Whereas in the case of conductors, electrons are mobile charges. Electrons are mobile charges. Mobile charges means the charges which are very easily movable. Such kind of charges we can call as mobile charges. In the case of conductors, electrons are mobile charges. Whereas in the case of insulators, the electrons or any charge given to the insulator will remain static. Any charge given to the insulator will remain static. So static charges are localized charges. So charges are not free in the insulator. For example, if you take any glass rod. So if a glass rod is rubbed with silk, then the charges on the glass rod will remain static. The charges on the glass rod will remain static. Okay. So example, there are large number of example for insulator, rubber, glass rod, paraffin wax, all these materials are insulator. Conductors, example for conductors, copper, aluminum and silver, all these are conductors. Large number of examples are there for conductors and insulators. So now let us study the behavior of conductors in an electrostatic field. Behavior of conductors in an electrostatic field. So there are few points that you have to understand. First point, the net electric field in the interior of conductor, the net electric field in the interior of conductor is 0. First point, the net electric field in the interior of conductor is 0. So even if the conductor is placed in an external electric field. So let us consider a conductor placed in an external electric field. So a conductor is placed in an external electric field. So this is external electric field applied. And this is conductor. This is end A of the conductor, this is end B of the conductor. Okay. When an external electric field is applied to the conductor, we know that conductor consists of large number of free electrons. These free electrons will experience a force. These free electrons will experience a force F is equal to minus E into E. This force is in a direction opposite to the direction of electric field applied, external electric field. So here, when a conductor is placed in an external electric field, the free electrons in the interior of the conductor will experience a force minus E into vector E, where small e is the charge of the electron, capital E is the external electric field applied, and this force is in a direction opposite to the direction of external electric field, that is the force is in this direction. As a result of this force, the electrons will move from the region B, the end B to the end A in the conductor. The electrons will move from the end B to the end A. As a result, the end A becomes negatively charged and the end B becomes positively charged. So due to the redistribution of electrons, the end A becomes negatively charged or the end B becomes positively charged, and this redistribution of electrons will create an electric field, will induce us an electric field. We call it as induced electric field, and this induced electric field will be in a direction opposite to the direction of external electric field. So here, when a conductor is placed in an external electric field, the free electrons, the large number of free electrons of the conductor will experience a force minus E into Ext, and this force is in a direction opposite to the direction of external electric field. As a result of this, the electrons will move from the end B to the end A. The electrons of the conductor will move from the end B to the end A. As a result, large number of electrons will accumulate at the end A, so end A becomes negatively charged, and end B becomes positively charged. And this redistribution of electrons will induce us an electric field in the interior of the conductor. It is called induced electric field, and this induced electric field is in a direction opposite to the direction of external electric field, and the induced electric field is, the magnitude of the induced electric field is equal to the external electric field, external electric field inside the conductor. The magnitude of the induced electric field is equal to the external electric field inside the conductor. Hence, the net electric field in the interior of the conductor becomes 0. The net electric field in the interior of the conductor becomes 0. See here. When an external electric field is applied, the electrons will move from the end B to the end A. As a result, the end B becomes positively charged and end A becomes negatively charged. And due to this redistribution of electrons, a induced electric field is created. We call it as induced electric field, and the direction of that induced electric field is opposite to the direction of external electric field, and the magnitude of the induced electric field is equal to the external electric field inside the conductor. Hence, the net electric field inside the conductor becomes 0. The net electric field in the interior of the conductor is 0. Understood? Next point, second point. Electric field just outside the surface of charged conductor. Electric field just outside the surface of charged conductor is, electric field just outside the surface of charged conductor is perpendicular to the surface, is perpendicular to the surface of conductor, is perpendicular to the surface of conductor. Understand this point? Second point, electric field just outside the surface of charged conductor. Electric field just outside the surface of charged conductor is normal to the surface of the conductor. So, if there is a charged conductor is there, then electric field will be normal to the surface. Electric field will be normal to the surface. That is the point. Okay. If electric field is not normal to the surface, if electric field is not normal to the surface, then electric field will have a component tangential to the surface. If electric field is not normal to the surface, at this surface, if electric field is not normal, then electric field will have a tangential component along the surface, and this tangential component of electric field will causes the electric charges to flow. That is, it will create a surface current. But here, if electric field is not perpendicular, at this point, then electric field will have a tangential component along the surface of the conductor, and this tangential component of electric field makes the charges to flow. That will create a surface current. But surface currents are not observed. Surface currents are not observed in electrostatic field. Surface currents are not observed on the surface of the conductor when it is placed in an electrostatic field. So, this shows that electric field just outside the surface of charged conductor is perpendicular at every point, is perpendicular to the surface of conductor at every point. Electric field just outside the surface of charged conductor is perpendicular to the surface of the conductor at every point. At any point if you take, the electric field will be perpendicular to the surface at that point. Understood? So, if electric field is not perpendicular, then it will have a tangential component. That tangential component will create a surface current, but surface current is not observed when the conductor is placed in electrostatic field. Hence, the electric field is always perpendicular to the surface of a charged conductor. Understood? This is second point. And third point. Net charge, the charge in the interior of the conductor, charge in the interior of conductor is 0. Charge in the interior of the conductor is 0, or net charge in the interior of the conductor is 0. Any excess charge resides on the surface of conductor. Here, net charge in the interior of the conductor is 0. Net charge in the interior of conductor is 0. Any excess charge is there. That charge will reside on the surface of the conductor. This is third point. First point we have studied, the net electric field in the interior of the conductor is 0. Second point we have studied, electric field just outside the surface of the conductor is perpendicular to the surface of the conductor at every point. Third point, net charge in the interior of the conductor is 0. Any excess charge resides on the surface of the conductor. So now let us consider a charged conductor. So now imagine a Gaussian surface. Just inside the outer surface of the conductor. Imagine a Gaussian surface just inside the outer surface of the conductor. And now, according to the Gauss theorem, the electric flux through this Gaussian surface, is given by, that is the surface integral of vector E dot ds is equal to q divided by epsilon naught. But we know that electric field in the interior of the conductor is 0. The net electric field in the interior of the conductor is 0. So therefore q divided by epsilon naught is equal to 0, or q is equal to 0. That is, the net charge in the interior of the conductor is 0. And if any excess charge is there, that excess charge will reside on the surface of the conductor. So here, let us consider a charged conductor. And now, in this charged conductor, imagine a Gaussian surface just inside the outer surface of the conductor, just below the outer surface of the conductor. According to the Gauss theorem, the electric flux through this Gaussian surface is given by integration of vector E dot ds. That is, we have studied in the first chapter, this electric flux. It is surface integral of electric field dot ds is equal to q divided by epsilon naught. And we know that electric field in the interior of the conductor is 0. That is, E is equal to 0. So therefore, if E is equal to 0, then the same thing becomes 0. So q divided by epsilon naught is equal to 0, or q is equal to 0. That is, the net charge in the interior of the conductor is 0, and any excess charge resides on the surface of the conductor. Okay. So next point. Fourth point. Electric potential is constant. Throughout the conductor. Electric potential is constant throughout the conductor. See this point, fourth point. Electric potential is constant throughout the conductor. So now, the electric potential inside the conductor as well as on the surface of the conductor will remain same. That is, electric potential in the interior of the conductor as well as on the surface of the conductor will remain constant. Electric potential is constant throughout the conductor. That means electric potential in the interior of the conductor as well as on the surface of the conductor will remain same. That is, electric potential does not changes throughout the conductor. So now, we know that the electric field intensity, how to prove this one? The electric field intensity is the negative potential gradient. We know that the electric field intensity is the negative potential gradient. So in the interior of the conductor, the electric field intensity is 0. In the interior of the conductor, inside the conductor, the electric field intensity is 0. So therefore, dV divided by dr is equal to 0. dV divided by dr is equal to 0. So differentiation of a quantity is equal to 0. Differentiation of a quantity, physical quantity, is equal to 0. That means that physical quantity is constant. This is the meaning of mathematics. Once you study the mathematics, you will understand the differentiation of a physical quantity is coming out to be 0. That means that physical quantity is constant. That is, electric potential is constant. V is equal to 0, 9. Differentiation of V, that is the differentiation of electric potential with respect to distance, is 0. That means electric potential is not changing with respect to distance. The meaning of this mathematical expression is that electric potential is not changing with respect to distance. Electric potential is remaining constant. That is what? Electric potential is constant throughout the conductor. If you take a conductor, so if you take r, distance from the center of the conductor, as the distance from the center of the conductor increases or changes up to the surface of the conductor, electric potential will remain constant. Electric potential will remain constant up to the surface of the conductor. That is, here the electric potential is same, here the electric potential is same, here also, here also, here also. If you take anywhere, the electric potential will remain same, not outside. Not outside. Outside the electric potential may be different, but inside on the surface of the conductor, the electric potential is constant. Hence, we can say that the surface of a conductor is an equipotential surface. The surface of a charged conductor is an equipotential surface. The surface of a charged conductor is an equipotential surface. Did you understood? Electric potential is constant throughout the surface of the conductor. Okay. So these few points that you have to study. First point, the net electric field in the interior of the conductor is 0. That means inside the conductor, the electric field is always 0. Next point, electric field just outside the surface of charged conductor is perpendicular to the surface of the conductor at every point. That is, these points indirectly we have studied while studying the that is properties of electric lines of forces. These properties we have studied indirectly while studying the properties of electric lines of forces. Okay, no problem. Electric field just outside the surface of charged conductor is perpendicular to the surface of charged conductor at every point. Okay. That is, electric lines of force are always perpendicular to the surface of a conductor. Okay. Net charge in the interior of the conductor is 0. Net charge in the interior of the conductor is 0. If any excess of charge is there, then that charge resides on the surface of the conductor. And the fourth point, electric potential is constant throughout the conductor. Electric potential is constant throughout the conductor. And next point, let us study the next point. Shall I remove all this? Okay. Okay, next point. Fifth one, electric field intensity due to the surface of, due to the charged conductor. Electric field intensity due to the charged conductor is directly proportional to the surface charge density. Electric field intensity due to charged conductor is directly proportional to surface charge density. Understand this point? Electric field intensity due to a charged conductor. Electric field intensity due to charged conductor is directly proportional to surface charge density. So now consider a conductor, consider a charged conductor. So now imagine a Gaussian surface in the form of cylinder. Imagine a Gaussian surface in the form of a cylindrical pillbox, such that some portion of the pillbox is inside the conductor. Consider a conductor. So imagine a Gaussian surface in the form of cylinder, and the some part of this Gaussian surface, that is cylindrical pillbox, is in the interior of the conductor, and a small part of the Gaussian surface is outside the conductor. So now there are three surfaces for this cylindrical Gaussian surface. So two circular surfaces, so two cross-sectional circular surfaces and one curved surface. Two circular surfaces, cross-sectional circular surfaces and a curved surface. Now the electric field in the interior of the conductor is 0, hence the electric field with the Gaussian surface which is inside the conductor will be 0, and the electric field due to the electric flux due to the curved surface, the electric flux due to the curved surface will be 0, because electric field intensity is perpendicular to this curved surface. The electric field intensity is perpendicular to the curved surface, hence electric flux due to the curved surface will be 0. So electric flux will be there only due to the circular cross-sectional area which is outside the conductor. The electric flux will be contributed only due to this circular cross-sectional area which is outside the conductor, that is electric field intensity, and the normal to this surface will be also in this same direction. So now according to the Gauss theorem, the integration of vector E dot ds is equal to q divided by epsilon naught. According to the Gauss theorem, vector integration of vector E dot ds, that is electric flux through a Gaussian surface, is equal to vector E dot ds is equal to q divided by epsilon naught. So now let us consider that the surface charge density of this conductor is sigma. The surface charge density of the conductor is sigma. Then we can write we can write the charge within this circular pillbox can be done as charge is equal to sigma into ds. Charge is equal to sigma into ds. So therefore this integration of vector E dot ds can be done as vector E integration of ds is equal to q divided by epsilon naught, and integration of ds can be done as just ds, that is surface area. So I will write it directly, vector E dot ds is equal to vector E dot ds or theta is equal to 0. So therefore EDS cos theta is equal to q divided by epsilon naught, and theta is equal to 0. So therefore EDS is equal to q by epsilon naught. And now the charge due to this surface charge density sigma can be written as q is equal to sigma into ds. So therefore EDS is equal to sigma ds divided by epsilon. So ds cancel. So E is equal to sigma divided by epsilon naught. So this is the electric field intensity due to the charged conductor. And since electric field intensity is perpendicular, we know that electric field intensity at every point on the surface of the conductor is perpendicular. So therefore that formula can be done as vector E is equal to sigma divided by epsilon naught into n cap. Vector E is equal to sigma divided by epsilon naught into n cap. This is the electric field intensity due to the charged conductor, and that is electric field intensity due to charged conductor is directly proportional to surface charge density sigma. Sigma is the surface charge density. Did you understood? This is fifth point. So these all are the 5 points that you have to understand. Once again I will repeat. First point, the electric field intensity in the interior of the conductor is 0. The net electric field intensity in the interior of the conductor is 0. And the second point, that is the electric field intensity at every point on the surface of a charged conductor is perpendicular. The electric field intensity on just outside the surface of a charged conductor is perpendicular to the surface of the conductor at every point. And third point, the net charge in the interior of the conductor is 0 and any excess charge resides on the surface of the conductor. And the fourth point, the electric potential throughout the conductor will remain constant. The electric potential throughout the conductor will remain constant. And the fifth point, electric field intensity due to charged conductor is directly proportional to surface charge density. Understood? So these all are the points that you have to understand. So when a conductor is placed in an electrostatic field, when the conductor is the behavior of conductor in the electrostatic field. Okay. So now we understood, just now we understood that in the interior of a conductor the electric field intensity is 0. So now there are certain instruments, certain sensitive instruments which need to be protected from electric field intensity. There are certain sensitive instruments which are needed to be kept away from the electric field intensity, or which are need to be placed at such a place where the electric field intensity is 0. Okay. So that can be achieved by using this concept, that is electrostatic shielding. Electrostatic shielding. Okay, let us understand. The process of electrostatic shielding. The process of protecting certain instruments from the effect of electric field. The process of protecting certain instruments from the effect of electric field is called as electrostatic shielding. The process of protecting certain electrical instruments from the effect of electric field is called as electrostatic shielding, and this can be achieved by using a halo conductor. It can be achieved by using a halo conductor. Consider a halo conductor. Halo means inside this there is no matter, it is vacant inside the conductor, so matter is not there, that is, it is a solid halo sphere. So this is charged solid halo sphere, so let us consider it as charged, no problem. So in the interior of the halo sphere the electric field intensity is 0. Hence if an electrical instrument, any electrical instrument is there, if that electrical instrument is placed inside the halo sphere, it will be protected from the electric field. So that is called electrostatic shielding. It is the process of protecting certain electrical instruments from the effect of electric field. The process of protecting certain electrical instruments from the effect of electric field is called as electrostatic shielding, and it can be achieved by using a halo conductor, because in the interior of the halo conductor the electric field intensity is 0. The electric field intensity in the interior of the halo conductor is 0. That means the electrostatic force acting on this instrument will be 0. Electrostatic force acting on this instrument will be 0 inside the halo conductor. What the idea? So this is called electrostatic shielding, and this is the reason why we say that during thunderstorm, so that is during thunderstorm, we have to remain inside the home, or if we are inside the car, we have to remain inside the car, just do not come outside the car. So, the metal body of the car will behave as a halo sphere. The metal body of the car will behave as a halo sphere, and it will protect us from the thunderstorm. It will protect us from the thunderstorm. So, that is called electrostatic shielding. Understood? So, this is next concept we will study in the next classes.